Good morning, everyone. So today we are going to start discussing partially observed systems. The specific model is also called POMDPs, but this refers to a specific type of partially observed systems. I'm going to be talking about I'm going to be talking about a more general model and see what's happening here. Just give me a second. For some reason, my notes are not loading for me. Okay, so let me start with an example. So last time we had considered this example of inventory management where we said that there is a stock that the warehouse owner owns and the dynamics are going to be equal to something like this. There is a per step cost which was a function of, so there is a cost for procurement and there was some holding cost for the amount of goods that were left in the warehouse. The assumption that we had made there was that the demand process W1 to Wt is independent. Right? Now, let me consider a variation of this problem where the demand depends on, demand is sometimes high, sometimes low, and it depends on the season, which can be high or low, and that's determined by a random variable we would denote by W0. So let's say W0 is a random variable, low and high, and my assumption is going to be W1 to Wt are independent, conditioned on W0. But W0 is not observed by the decision maker. Okay? So the model is same as before in all other aspects, except the whether we are in a high season or a low season, the decision maker does not know. It still has to act based on its observation and actions. And in this case, I'll denote HT as the history of observations and actions, which in this case would be W1 to T minus 1 and A1 to T minus 1. And the decision problem I'm interested is same as before. I want to choose AT to be some function of the history at time t. What has changed is that this history is this. In particular, it does not contain W0. Okay. If I had W0 in the observation of the decision maker, this would become a fully observed decision problem. We have already seen how to solve this, but we look at this partially observed system. And for the beginning, I'll focus on the terminal cost setting. So there is a terminal cost which I can compute as the sum of the per step costs, but we'll derive a dynamic programming decomposition which would be based on the terminal cost, and then we'll do the specialization to per step cost. Is the model clear to everyone? Ft will be Markovian, but at the moment, I'm not worried about the Markovianness of the model at all. Okay? I just want to see, this is a decision problem. If I can understand how to solve general problems of this type, we'll then specialize to what happens when Ft is Markovian. Sorry, this is finally working, so give me a second. Okay. So, I want to go back to the decision trees that we drew and draw a decision tree which captures everything that is happening in this system. So, what I am going to do is at the beginning nature acts and chooses the value of W0. Okay. This W0 is either low or high. Then the decision maker has to act. I'll draw this in a slightly different way. Let me draw it like this. This is low or high, and then the decision maker has to act. Okay. At this stage, the decision maker does not know whether the state of nature is low or high. So, I am going to capture that by drawing what's called an information set. Okay. And this really is the history at time 1, because in something has happened in nature. Nature has realized whether the demand is going to be low or high, but the decision maker does not know. So, that means although there are two decision nodes in this information set, the decision maker has to take the same action in both of them. I cannot pick to buy low goods here and buy high goods here, right. There are multiple actions in these cases. The decision maker will have to take the same action in both of these cases. Okay. Once the decision maker does that, it is nature's turn to move. Nature knows the trajectory that has led to a particular node. So, nature can pick a different action on the top node versus this node, right. So, if I look at these two nodes, let me use a different color. So, if I look at this node and this node, both of them correspond to the case that the decision maker took the same action, but in these cases nature has taken different action. Okay. I am not imposing any restriction on the uncertainty realized by nature. These two can have different distribution, in general would have different distribution, because in this model my assumption is either the demand, it's a low season or a high season, so low demand will have different distribution in these cases. Okay. Once this is realized, there would be multiple outcomes here, and this gets now a bit tricky to draw. So, let's see this. So, I am going to be a bit careful in trying to keep track of a particular trajectory. Let us look at this trajectory and this trajectory. Notice what has happened is this trajectory W0 was low, agent chose low, nature chose low. In other trajectory, the first action was 1, agent chose something, nature chose something, right. At this stage, the decision maker has observed realization of this variable and the realization of this variable, but the decision maker did not observe the realization of the first variable. So, the decision maker cannot differentiate between these two nodes. So, I am going to draw an information set around these, and similarly I will have an information set around all possible. There will be 4 different information sets here corresponding to different pairs of histories, which differ only in their first step. Okay. And continuing this way, I can draw the tree completely, and at some stage I only have leaf nodes where I have some cost, and I can write down what is the cost of all of these leaf nodes. So, this is going to be my general model for modeling a system with partial observation. This was a simplistic model. I will take a model which is slightly more general than that. Let me describe that model. We will then see how do we do dynamic programming over that model, and then we will specialize that model to special cases to get a more efficient dynamic program. So, in general, I can think of a partially observed system as an input-output system. It has 2 inputs, a stochastic input Wt and a controlled input WT, and it gives me one output, and I'll write it as t plus 1 just to clarify that when input WT and AT is given, at that instance, I'm calling that instant time t plus 1, the output is yt plus 1. Okay? And my decision maker, so this is my system, this is my agent, and now my agent observes the output and uses that to choose the control input, and I'll assume that the history of information available to the decision maker is everything it has seen in the past and everything it has done in the past. This assumption is super important for the decomposition that we are going to present. That this is sometimes called perfect recall. I can only do a dynamic programming decomposition if my system has perfect recall. Okay? And the reason for this will become clear once I write down the dynamic programming decomposition. As before, we assume that the system runs until certain time, and my final outcome is going to be the history at time, is going to be everything that has happened until time t. So I'll say the outcome is W0 to t, A1 to t, and Y1 to t. Okay? This is everything that happened in the system at the end of t time steps, and then I have a cost which is a function of the terminal of the outcome of the system. Okay? So what I'm changing is, in this type of a model, I have a trajectory of everything that can happen. In this model, the agent was able to observe everything other than the first thing. So its observation at time t is WT minus 1. In general, I can have a bit more elaborate thing. It becomes harder to draw trees explicitly for a general model like this, but you can visualize that that's my decision-making process. And what I'm interested in is to choose a policy pi, which will be pi 1 to pi t, where AT will be chosen as pi t of HT in order to minimize over all pi the performance of the policy, where the performance of the policy is defined as the expectation under pi of the outcome that I get. Okay? And again, what do I mean by expectation under pi? So a policy is now something which will tell in this decision tree how should the agent act at every information set. Right? So this policy should tell me what to do here, what to do here, and so on. And it must do such only based on the history of observations. So on the multiple trajectories which are part of an information set, it must take the same action. Okay. Is the problem formulation clear to everyone? Okay. So the first thing that I want to emphasize is, compared to what we did in the fully observed case, in the most general fully observed case, the partially observed case is not conceptually not any harder. Okay. So what was our idea there? In the fully observed case, I went to the terminal nodes. Whenever I had a chance node, I folded the chance node back, and when I had a decision node, I did the optimization according to the decision node. My claim is that the same procedure will work in this case. Okay. However, in that case, I did not really give you a complete proof of why that was optimal. I just gave a hand-wavy proof. In this setting, it's important to see why that decomposition gives me the optimal policy. So I'm going to do a slightly more elaborate dynamic programming decomposition so that it is clear why the way we were writing dynamic program is going to work. Okay? So, let me start by looking at a policy. Something fell. Let us do policy evaluation first. So, rather than doing dynamic programming, I will start by defining these objects. I will say for a given policy, the value function at time t given history ht is the expected value under policy pi for the terminal cost conditioned on ht equals to little ht. And the way I want to interpret this is as follows. So, let me take this decision tree. I fix a policy pi, which means I tell you at every information set what action should you take. As part of the problem specification, I need to give you a joint measure on all the primitive random variables. So, I have a joint measure on W0 to Wt, and I know at every decision node which branch I will take, and at every chance node what will be the probability distribution of all alternatives. This gives me a probability distribution on all possible outcomes. Okay? So, once I fix a policy, I have a measure on the outcomes. I also have measures on every node on this tree. So, when I take a particular history, I can compute the measure on, I can compute a joint measure on this history and the outcome, and from that joint measure I can compute a conditional probability, and this is the conditional probability according to which I am tweaking this expectation. Okay. Now, the reason why perfect recall is important is that I can do the following. I can write this as expectation under pi of the expectation under pi, the cost of OT conditioned on the random variable ht plus 1 conditioned on ht equals to little ht. Okay. This is the smoothing property of conditional expectation. I am conditioning on ht plus a bunch of random variables here. So, when I do this nested expectation, I will recover this. I can only do this if the information available to the decision maker at time t plus 1 was more than the information that was available at time t. Okay. Once I have this, this is really expectation of v pi t plus 1 of h t plus 1 conditioned on h t equals to little h t. Okay. So, when I have perfect recall, irrespective of whether I have full state observation or not, I can write down a recursion for computing the policy evaluation of a value function. Okay. This will be something which will start at v capital T of h t to be equal to expectation under pi of c of the outcome conditioned on h capital T equals to little h t. Okay. Now, once we agree that this is the right way to do the decomposition, I start with a terminal expected cost to go under, this is under policy pi, and then I do this recursion to compute it backwards. I am going to now go and write this in 2 steps, just because that's how we have been doing dynamic programming, and this will make my analysis slightly easier. So, I am going to take this dynamic program, I am going to write this as q pi capital T of h t a t to be expectation c of o t conditioned on ht equals to little ht and at equals to little at. There is a key assumption here, which is that although I am writing it as q pi t, this expectation will not depend on pi. Okay. So, let us go back and check what my outcome was. Right? The outcome is this, this and this. My history would be y12 capital T, T and a12 T minus 1. So, when I add the action, I am conditioning on these two objects on the realization of this. Okay. So, this object will not depend on the choice of measure. This is not super clear just from the definition. In the second half of this lecture, I will take a specific model, do some calculations, and will turn out then when we take conditional expectations of this form, they will be independent of the choice of the policy. This is super important in order for me to do optimization. Then I am going to define v pi t of ht to be equal to q pi t of ht pi t of ht, and we will do q pi of t is going to be the expectation of v pi of t plus 1 h t plus 1 conditioned on ht equals to little ht, at equals to little at, and do v pi t of ht to be q pi t of ht pi t of ht. Okay. Doesn't work. Yeah. Yes. Yes. So, that is why I am taking a posterior distribution on W0 and I will average according to that. Okay. So, the point is once I observe some parts of this tree, I can look at what is the, so for instance, suppose I was at this information set. I know what is the probability of receiving this given the history of things that I have received. Therefore, I can say what is the probability of this versus this given what I had observed. Okay. So, I can do that type of calculation in order to compute these conditional probabilities. So, for now the view I am going to take is that I am going to find the optimal policy using dynamic program, and dynamic program is what it is. Okay. Later on in tomorrow's lecture, I will come back to this question and say that the type of learning that you are describing can be thought of as a specific type of approximation that I am doing in order to figure out what my optimal policy should be, and we can look at that and take the approximation bounds that we have derived to get some form of approximation errors if I do these types of schemes. Other questions? Okay. So, again, the reason I did this in this level of detail is to basically point out that I require the perfect recall in order to derive this dynamic program, because next what we will do appears like the same thing, and one can get the impression that this thing will work under any assumption, but this is our key modeling assumption here. Okay. So, now how do I find an optimality dynamic program? I'm going to do the same recursion, except at this point, I'm going to replace policy evaluation by policy optimization, right? So I'll not write this completely in full, but what we'll be doing is only change is I'll have to define V star t of ht to be equal to minimization over all actions of q star t of ht and at. Okay. Now, and I'll say pi star t of ht is the argmin of this object. Okay. In particular, this means that V star t of ht is going to be equal to V pi star t at ht. I can show that recursively going backwards in time, because when my policy is equal to the minimizer here, these two recursions are the same. Okay. Now, one other thing to note in order to sort of complete the optimality proof is to realize that the performance of a policy pi is the expectation of the value function at time 1. Okay. This is under policy pi. Because history 1 has some distribution. In the example that I gave, it is just whether nature chose 0 or 1. I don't see anything in that case, but sort of I'll take the, I could have some observation at time 1. I average over that observation, and that gives me the performance of the policy. Now, the reason why this policy is optimal is that I can now show by backward induction that this object V star is going to be less than equal to this for all pi. And the reason is kind of obvious. It's the same argument that we did in the full observation case. The terminal q functions are identical. When I go to this guy, in one case I choose a particular action, in the other case I choose the optimal action. So the optimal value function will be a lower bound on this. And when I get here, by monotonicity of expectation, I get that the same thing will be true for the q function, and then this thing here. Okay. So my proof remains the same, and therefore I will get that pi star, which is equal to pi star 1 up to pi star t, is optimal. So if I have perfect recall, in the most general setting, partial observability or full observability is conceptually not any different. The difficulty is in partial observability, computing these guys requires more effort. Okay. So computationally, I may have to do a lot more stuff in computing the conditional beliefs here. In the case of full state observation, we really only need the probability of Wt given W0 to t minus 1. Anything else does not make an impact. Okay. But here I'll have to compute conditional probabilities and then do the averaging. Any questions? So let me do one simplification that we did in the fully observed case. I want to say what happens if I have a per step cost, right? Like in this example, there was a cost that was being incurred at every time, and I want to see how can I write down the dynamic programming decomposition when a cost is being incurred at every time. And to do so, I'm going to assume that in my system, at this time instance, when I have given the inputs At and Wt, the output also contains a random variable Ct, which is the cost at time t. So, in general, the cost at time t could be a function of all the inputs that this system has received. In principle, I can also allow it to depend on yt. That doesn't really change much. Okay. So, I can say the cost at time t really, if I think about it formally, is a random variable which is measurable with respect to everything that has happened until this time. Okay. So, let us consider the case when C of the outcome was equal to C1 till C capital T. Okay. How does my dp change? We will do the same thing we did in full observation. When I go here, there is C1 to C t minus 1, and I will basically ignore those. Okay. In the fully observed case, I could bring them out of the expectation. In this case, I cannot. I am not assuming those guys are only measurable with respect to history. Okay. But it will turn out it does not matter, because it will come out as a conditional expectation, and that gets absorbed in the previous thing. So, in this case, I can write the following recursion. I can define q star t of, or actually let me do what we did last time. Let me define v star t plus 1 of the history at t plus 1 to be identically equal to 0, and then I can just write everything once. So, I can say q star t of h t q star t of h t a t is the expectation of C t plus v star t plus 1 of h t plus 1 conditioned on h t and a t, and then I will define my value function to be the optimal here. Okay. So, this part is same as the simplification that I had done in the fully observed case, and the proof why this is optimal is same as what we did last time. I can show this is a valid policy evaluation function. If I look at, if I define the value function to be the cost to go rather than the total cost, I will define the value function to be the cost from time t onwards, and we will get the same proof argument. Okay. So, the question now is, for the setting of full state observation, I imposed few more assumptions on this model, and I said I can get a much simpler dynamic programming solution, which only depends on some compact state. So, the trouble with this decomposition is that my history is increasing over time. So, when I want to do something, my complexity is going to be become more and more as a function of time. In particular, if I start storing this, I will have to start storing like a rectangular array that history is always increasing over time. So, the complexity is increasing quadratically over time. I would like something where I can get like linear complexity over time. So, I would like to have a representation of this history which is not growing over time. Okay. So, can I find such a state for dynamic programming? So, I am going to now say that if I can find a way to compress the history such that certain properties are satisfied, then I can have a much simpler dynamic programming. So, this is the notion of information state. And in all this, I am going to be using script HT to denote the set of all histories at time t. Okay. So, I am going to say that I have an information state generator. This is a collection of functions sigma t, where sigma t maps the history at time t to some space. Okay. Formally, I need this to be a space so that I can talk about probability distributions on this. In the discussion that I am doing right now, I am kind of implicitly assume this is discrete, but this can be this in the examples that we will do, this can be a continuous state. In general, I am going to sort of technically do the analysis where this is a Banach space, so I don't have no issues defining probabilities on this. It can be relaxed further, but then I have to be careful in how I define probabilities. Okay. So, I am going to ignore all the technical stuff and simply say I have a state sequence of functions which map history to states, and for continuous variables we are going to assume all the measurability properties and so on will remain satisfied. Now, it is called an information state generator if two properties are true. Property P1 is that I am going to now define ZT to be what I get when I compress the history at time t, and this is that ZT is sufficient for performance evaluation. That means that when I take the expected value of the cost at time t conditioned on history at time t and action at time t, I am taking a slightly shorter notation. I am not going to keep on writing capital HT equal to small ht. This means that I am conditioning on those events. Okay. This should be equal to the expectation of Ct conditioned on Zt equals to sigma t of little ht and at. Okay. And the key assumption here is that this thing does not depend on the policy. Okay. So, the first property that this state should have is that when I look at what is the expected cost at time t conditioned on what I have observed until time t and what I do at time t, I can compute that expectation simply as a function of my compressed state and actions. Okay. Yeah. In general, I have imposed no assumption on my cost. Right? I just said cost is some measurable variable. Yes, I don't want to. I want to do this generally in every time, because once I'm doing other things, this will not always be true. So, when I'm defining these conditions, in some of them the left-hand side might not depend on the policy, but in others it do. So, always I'm going to write policy dependence on the left-hand side. P2 is it is sufficient for predicting itself. Okay. So, that means when I look at the probability distribution of the next information state conditioned on HT and AT, sorry, this should be true for all HT, AT. This should be equal to the probability distribution of ZT plus 1 conditioned on ZT being the compression of history and AT. Okay. My claim is that if I have an information state that satisfies these two properties, then I can write down a dynamic programming decomposition in terms of ZT. Before I give a proof of that and formally state that, let's just go and take the case that we know how to solve, which was an MDP. Okay. What happens in the case of an MDP? My history, so for an MDP, my history was equal to S1 to T and A1 to T minus 1. Right? If I want, I can also add the W's, because I was observing everything that has happened in the system in the past. Okay. Now, I can think of my history compression function as something which takes HT and maps this just to the current state. My assumption in that case was that Ct was some function of the state at time t and the action at time t. Okay. So, it is clear that this equation holds. When I look at the cost condition on the history and actions, there is nothing random here. I will just get a scalar number which is the cost function evaluated at the current state and action, and that is what I will get in the right hand side also. Okay. And the second property was that when I look at the probability of Ft plus 1, recall this was some function of Ft, At and Wt conditioned on Ht and At. By my assumption that Wt was independent across time, I get that this object is really the probability of Ft plus 1 equals to some function of Ft, At and Wt, and this guy will be the same whether I condition just on the current state and action or the entire history, because the distribution of Wt does not depend on any of the things. Yeah.
Under what conditions does in some sense useful information state generator exist? Like one trivial one is identity filters. Then in what cases can you actually compress
I am going to show in general I can come up with a belief state which is always an information state, and as you mentioned, history is always an information state. Beyond that, it will depend on the model. There is no universal information state, but I am going to give examples of different models where I can have much simpler information states. All right. Yes, so my point is, it is this, and I can say this is equal to the probability of the same thing conditioned on Ft and At as well. All these things are the same, right? Because the only random variable is Wt, and that is independent of what has happened in the past. Okay. So, we know that in an MDP, the current state was an information state, and in an MDP, I could write down a dynamic program based just on the current state. The claim that I am making is that for a general partially observed system, if I have an information state, I can write down a DP in terms of the information state. So, notice what is going to happen. I am going to define Q star, let us just do V star t plus 1 of Z to be equal to 0, and for all t, we will do Q star t of Z is equal to the expectation of Ct plus V star t plus 1 of Z t plus 1 conditioned on, let's call this guy ZT, ZT and AT. Sorry, this should have been ZT and AT also. Okay. And the value function will be the optimization of this. So, I mean, in principle, I should call these a different variable name because Q star was functions with histories, but it should be clear from the notation whether I'm talking about history-dependent Q functions or just information state-dependent Q functions, right? And the proof is kind of obvious from these two statements. So, I know this terminal value function is equal to the terminal value function there. So, I can recursively show the following. I can show that the Q function at any time, function of any history and action, is equal to Q star of the compression of the history and actions, and the value function at any time as a function of history is equal to the value function of the compression of the history. Once I show these two things, I will get that I prove this by backward induction. This is true at the terminal time, and as I go backward, distribution of ZT plus 1 conditioned on all the history and actions can be replaced by this. Distribution of the expectation of this guy can be replaced, and therefore I can do a backward step and show that if this is true at time t plus 1, it should also be true at time t. Okay. So, it's a very, very simple observation. If I have in statistics, this is something which is known as a sufficient statistic. Okay. If I have a sufficient statistic for evaluating the expectation of the per step cost, and that sufficient statistic is recursively updatable, okay, then I can write down a dynamic programming decomposition in terms of that sufficient statistic. That is a sufficient statistic for dynamic programming as well. Okay. Yes. Yeah. Yes. This is true for everything. Yes. So, fully observed are a special case of partial observation, right? So, this is true for every system. The only assumption that I have, there are two assumptions that I have made. One is that I have perfect recall, and second is that my cost is decomposable. Okay. If my costs were not decomposable, I can basically say this should hold at the terminal time, right? And that's it. Yeah. In principle, so in something like linear systems, people will talk about, not necessarily for dynamic programming, but for a state space representation, there is a lot of discussion about what is a minimal state space representation. I personally feel that defining the notion of minimality is, you have to be a bit careful. Okay. Let me give an example for this. I have this example in the notes in one of the previous things, but I did not discuss this here. So, let's say I have a sensor which is observing an autoregressive process, and the sensor can decide either to transmit its observation to a receiver or not. Okay. And when it transmits something to the receiver knows exactly. If it does not transmit, the receiver has to decode what was in the packet. And I'll think of what is the error from what is received at the receiver, and one model can be that the error process has the following dynamics. So I'm saying my process that I was trying to observe was some kind of an autoregressive first order process. I take a sensing, send it, and the receiver will get it, or the receiver will not get it. And let's say my per step cost is s squared plus lambda times a. So if I do not decode correctly, then I have to pay a cost of s squared. And if I decode, and whenever I communicate, I have to pay a cost which is equal to lambda. Now, if W has a distribution which is symmetric, I can show that absolute value of S is an information state. In particular, what that means is, if I were solving this dynamic, this is a MDP, right? But if I were solving this dynamic program in the original state space, my value function as well as my optimal policy will be even functions. Okay? And therefore, like this is an information state, means that I can just look at the absolute value of that and I'll have the same value function. Okay? But you see, so in some sense, this is a smaller information state than this full state, right? At least I have folded my state space into half. But this folded thing has a much more complicated dynamics, right? This has linear dynamics. So now imagine a case where like this is continuous, I was trying to solve it with, let's say, taking something with polynomials, right? I say I'm going to take, I don't know what they're called, the Bessel polynomials, an orthogonal family of polynomials of degree 10 to find the solution for here. It will be much easier to compute the things for this than compute what happens when I have this this folding effect taking place, right? So I can have a smaller storage requirement, but this will make solving my dynamic programming harder. So we have to be careful if we pose the question of what do I mean by a minimal information state. So is it minimal for the purpose of storage, or is it minimal for the purpose of my computational effort required to compute the policy, or there is a trade-off between the two. Oftentimes in a real system, you would do this based on sort of your engineering intuition, right? So you know something about the system and you would use that to say this looks like something which is useful for me. Formally defining minimality becomes complicated, especially when I'm going to continuous spaces. Okay. Other questions? Okay. So let me spend some time giving a few examples, but before that, let me make one point. Where should I erase? Let me erase this guy. Now, given a system, this is reasonably easy to verify. I will know what the cost function is. I will have some intuition of this I want to check is an information state, and I can check whether this condition holds or not. This one can be complicated. So I'm going to give you sufficient conditions for this to hold. Okay. So suppose I have an information state. I have not made this assumption here, but suppose there exists some function so that my information state is recursively updatable. And second, that when I look at the probability distribution of yt plus 1 conditioned on ht and at, that is equal to the probability distribution of yt plus 1 conditioned on zt equals to this, and this thing should not depend on the policy. My claim is that these two conditions imply P2. Okay. And the intuition or the proof is relatively straightforward. What I want to show is that I look at this object, right. So, I will give a sort of a hand wavy proof, but it is not too difficult to make this precise. I look at probability of Zt plus 1. So, let us say Zt plus 1 belongs to some set conditioned on Ht and At. This is equal to the probability, and I am not writing this pi dependence everywhere just for simplicity, of little Zt Yt plus 1 At belongs to B conditioned on Ht and At. Okay. I can write little Zt here because it is a function of the history. So, I know what Zt is. At I am conditioning on At, so that is a value. So, the only random variable is Yt plus 1. Okay. So, if I have recursively updatable form and I know Yt plus 1, then I can have that this will be basically probability of this whole thing conditioned on Zt equal to sigma t of Ht and At. So, if I have a recursively updatable state which can predict the next observation, which is sufficient to predict the next observation, then I can write a dynamic programming decomposition based on this. Okay. I want to argue that this is stronger in general than something like this. No, Yt is my observation. No, you remember my model was there was an observation Yt at time t. That is my observation at time t plus 1. In the general partially observed model right now, I am making no assumption about S. I have not said anything about a state space model so far. It is just some system where I give an input Wt minus 1, At minus 1, I get Yt, I observe Yt and I take actions. Okay. So, what I am saying is what I observe at the next time should be a function of what I have of my information state. If I can predict the next observation, then clearly I can predict the next information state as well, if the next information state was recursively updatable. Yes. Okay. So, I am saying what I want to show is if P2A and P2B holds, then I get P2. So, I start with the left hand side of P2. What is the probability distribution of the next information state lying in some set given history and action? I know Zt plus 1 is this function, and this function lying in B, it has of 3 variables. Zt is a realization because I know Ht and this is a function of Ht. At is a realization because I am conditioning on that. So, the only random variable is Yt plus 1. And my assumption is that the distribution on Yt plus 1 conditioned on history and action is same as the distribution conditioned on the information state and action. So, I make that change, and what I have shown now is that the distribution of Zt plus 1 conditioned on history and action is that same distribution conditioned on information state and action, and therefore, I satisfy P2. Okay. So, let me give an example to show why P2 can be much like why P2 is much better than P2A and P2B. So, this is sometimes called the noisy TV problem. So, suppose I have an MDP where my state space consists of S1 comma S2. My dynamics are, or let me write them as S1 and S2. My dynamics are probability of S1 t plus 1, S2 t plus 1 conditioned on S1 t, S2 t and AT decomposes as follows. So, I can control the evolution of the first component of the state. The second component of the state is doing whatever it is doing. It is just a random walk. Okay. And my per step cost is equal to some other function of S1 and A. Okay. So, I have a system where there is part of the state which is just a random walk. I observe that thing, but it has no impact on my cost. Okay. The reason it is called a noisy TV problem is that in the reinforcement learning literature, people use this as a benchmark, saying I have an agent which is trying to navigate in a room. I have a TV on the wall which is just showing static noise. If I want to learn what is everything that is happening in the world, I have to figure out what's happening with that random noise. But clearly, that thing has no impact on my evolution, right? So, if I try to find a information state using properties P1 and P2, it's not hard to see that F1 is an information state. Right? Because it's sufficient for evaluating the per step cost and it's sufficient for predicting itself. There is part of my state space which I observe. This could in fact even be dependent on AT, it doesn't really make a difference as long as it does not impact the cost. Now, if I try to find something which is sufficient for this and this, S1 is not sufficient for predicting the next observation. Next observation is both components of the state, right? So, this is asking for something which is much, much stronger than just being able to predict the payoff relevant component of the state, right. Here, I am trying to say all observations, while I only care about things which are going to affect how my system is going to evolve. Yeah. I am not sure about that. In fact, I am quite confident that that would not be the case, because you see, let me think about it offline, but my intuition says that I cannot get rid of this if I want to predict observations. No, but you see, for the dynamic program, I'll have to get the distribution on ZT plus 1, right? So, if this is not recursively updatable, if this, in general, this will be HT, YT plus 1 and AT, right? So, I can't get rid of HT in my dynamic program. No, you can only figure out the distribution of, you can't throw away HT. No, because you see my dynamic program, I am interested in looking at the expectation of V t plus 1 of HT plus 1 given HT and AT. Okay. And I want to argue Z is sufficient for this, and then I can get a distribution of Z. If I don't have this recursively updatable thing, Z is just some arbitrary function of the history, then I'll not be, so maybe through induction I have shown that this I can replace by this guy, and I can write this as Vt plus 1 of sigma t of Ht plus 1. Right? But unless I have some way of compressing the past history here, I'll not be able to throw the history. Even if Yt plus 1 I can predict, I need to keep track of the history here. So if I want to throw the history, I need to say that I could have compressed the history with just Yt. Let's take this offline. Okay. All right. So let me give a few more examples. So this one is interesting. This is delayed observation. So suppose I have an MDP. Let's go back to this inventory control type of problem, but I don't get to see the realized value of state instantaneously. So suppose my observation at time t is the state at time t minus d. Okay. So the history available at time t is the state from time 1 to t minus d and the actions from time 1 to t minus 1. And this is an MDP, so my per step cost is some function of St and At. What is the information state of this model? Okay, let's start with the simplest case. Suppose delay was equal to 1. Is the last observed state sufficient? So one suggestion is I should take, if d is equal to 1, I should take Zt to be equal to Ft minus 1. Okay. Let's check what I need. I would have to form a probability distribution on. So to compute the expected cost, I really need a probability distribution on the current state conditioned on the history, which is f1 to t minus 1, a1 to t minus 1, and at to be equal to the probability distribution on ft conditioned on ft minus 1 and at. Right? If this is true, I could say that this is sufficient for evaluating the current cost. Okay? I don't really care about at, so let's ignore that here because this is something in the future. Is this statement true? I need at minus 1 as well. Right? Just can't take the last state because I have acted in the world. I need to know how I acted in order to compute the distribution of the current state. So in general, for general d, it would be the state at time t minus d plus all the sequence of actions that I have done since then. So when I have delayed state observation, I can choose the state that I observed last, all the inputs that I had given to the system during that time, and this will be an information state. Now, let me give the example of the information state here. From that, we will go to general POMDPs and see what happens to an information state there and look at few more examples. Okay. In this example, so recall the thing was it's either low season or high demand season, and I don't know whether it is a low demand season or a high demand season, but I see everything that is being realized. What's the natural way to solve this problem? Average with respect to what? So you see what happens is the distribution of demands that I observe. So demands that I observe tells me something about whether this was a low season or a high season. So, I can keep track of my belief on W0. So, for this particular example, I can keep track of the probability distribution of W0 conditioned on the history. Okay. This is going to be equal to probability distribution of W0 conditioned on W1 to t minus 1. Okay. So, if I know the joint distribution of all these variables, I can use Bayes' rule to figure out what this belief should be. Okay. My claim is this is a information state for the problem. Okay. Why is that the case? If I look at the current cost. So, let us see, the current cost was P times A plus some holding cost of S plus A minus W conditioned on W1 to T, A1 to T. This is the object that I am interested in. This is AT. Okay. Knowing the values of W's and A's, I can figure out what the current state is. I started with some state and this is evolving according to certain things. So, this guy is known, AT is known. The only unknown quantity is, sorry, this is W T minus 1 at this stage. Only unknown quantity is WT, right. So, to compute this expectation, I need to know the probability of WT conditioned on W1 to T minus 1. Okay. And therefore, if I have this belief, I can just use Bayes' rule and I can, so first I can use law of total probability and I will say this is probability of W0 conditioned on W1 to T minus 1 and then the probability of WT conditioned on W0 W1 to T minus 1. Okay. In the simple case where condition on W0 everything was independent, which was my assumption, I can get rid of this quantity and I have a way for, given the belief, I have a way for computing this distribution. Okay. So, this is going to be ending up being some function of, let us call this guy belief at time t, of the belief at time t and the action at time t. Okay. So, this satisfies P1. Let us now look at P2 and you see P2 would mean I need to look at this condition on WT. And from the fact that I can do this, it should be clear that I can basically write probability of W0 condition on W1 to T as some function of probability of W0 condition on W1 to T minus 1 and WT. This is the type of thing that one does in nonlinear filtering. Given a latent variable, I am observing a process and I want to figure out the distribution of that. So, I will write the nonlinear filtering equation here. Okay. So, in this example, the belief of the uncertainty conditioned on everything that I observe is a information state for solving this problem. Okay. This is something which is true in general. So, let me now give the description of a general POMDP. So, this is how POMDPs are traditionally introduced in the literature. That is one way to do that. Okay. This is not the only way to do that. Okay. But yes, it's not just what you don't know, the payoff relevant part only. I don't need to estimate everything that I do not know. Okay. In this example, this turned up to be the only part, but let us say I had a completely irrelevant random variable, I don't want to estimate that. It's only because this impacts my cost that I am concerned about something. So, a standard because when I presented this model, I was saying that these are conditionally independent given W0. That was the assumption that I had made. If I had not made the assumption, I would need one more Bayes rule type of thing to take care of this. So this is the standard POMDP model. And what this says is, let me start with an MDP. Okay. So I have a state space, action space, P and C. And I'm going to assume that I do not observe the state, rather I have some observation space, and at every time I get yt, where I am given probability of yt conditioned on st. So I observe some noisy version of the state, and I want to choose a policy to minimize the expected value under pi of the cost of ft and at. Okay. Now, this is a special case of the type of models that we have been considering. What we can show is that for this model, if I write what is called the belief, Bt of S will be the probability distribution of ft equals to S conditioned on y1 to t, a1 to t minus 1. This is an information state. I am going to do a few things to show this is an information state. First thing to realize is I have to look at what happens to its dynamics. And what you can do is you can show the following. I will not write this down completely, but just give the intuition here. Let us think of probability of ft plus 1 conditioned on y1 to t plus 1, a1 to t. If the action part was not there, okay, I can go from probability of ft conditioned on y1 to t to probability of ft given y1 to t plus 1 using nonlinear filtering equations. Okay. I am getting one additional noisy observation of this. Okay. So I can do this using nonlinear, or let me do it slightly differently. That may be slightly more natural. I can go from here to ft plus 1 given y1 to t. Let us add the actions back. So if I had a belief on the state and I tell you what the current action is, from the dynamics of S, I can compute what the distribution is. Okay. And now if I get one more observation, I can compute through nonlinear filtering what this distribution would be. Okay. So I can go from the belief at time t to the belief at time t plus 1 as a function of the observation at time t plus 1 and the action at time t. So I can write down a nonlinear filter which says that the belief at time t plus 1 is some function of the belief at time t, y t plus 1 and at. Okay. The key thing in this thing is, if we write it down explicitly, and I have done it in the notes, that none of these expressions, that this function does not depend on the policy at all. Okay. And this is important. Okay. Once I have that this function does not depend on the policy at all, that means that this satisfies P2A. Right. This is equivalent to P2A. I can now show that from this object, I can get probability of yt plus 1 conditioned on y1 to t, a1 to t, right? Because I know what is the observation as a function of the state, which means that I can get this object from my belief. So, that means that I also satisfy P2B. Okay. And finally, the fact that this belief can be recursively updated without knowing the policy means that the belief itself does not depend on the policy. I start with the initial belief, which will be policy independent, and I keep on recursively updating it, and I'll get a sequence of beliefs which are policy independent. So, I can, from this belief, I can write down the expectation of the cost of Ft and At conditioned on Ht and At as a function of the belief and action, and since this belief does not depend on the policy, this function does not depend on the policy. Okay. So, I have a way of, so this means I get P1, right. So, this belief, so only thing I have not done here is explicitly write out this equation for the nonlinear filtering, but I get that this belief satisfies all the three properties that I need for an information state. Therefore, this is an information state. Okay. Now, so I can write down a dynamic program based on this, but at the face of it, this is a ridiculous thing to do. So, the problem that I started with, like this example also, I can make the same claim here. I started with a problem in which my histories were discrete. They were increasing with time, but they were discrete. I have converted into a problem in terms of belief, which lies in a simplex. Okay. So, it is not increasing over time, but I have gone from a finite space to an uncountable space. Okay. So, is this a simplification? The reason why this particular simplification is so popular is because in the history space, I had no natural metric on my space. Now, I have something where like a quantity like this is going to be affine in my belief. This has very nice structure. It is like ratio of two affine functions. So, overall, what one can show is that if you write down the dynamic program in terms of belief, the dynamic program is going to be piecewise linear, and this is cost minimization. So, piecewise linear and convex. So, typically my value function would have a shape like this if I am drawing it as a function of the belief. And this is exploited in all numerical algorithms to solve the partially observed MDPs, that rather than doing some stupid thing like quantizing the beliefs, what you do is you exploit the structure of this and you say this is the minimum of certain affine hyperplanes. So, I am going to keep track of these hyperplanes and update my value function over time using these hyperplanes rather than explicitly keeping track of what is the value of the belief at a particular time. Okay. So, going to a larger information state can be useful because it provides you structure that can be used in the computational algorithms. Okay. Now, once I have this belief, I can ask, are there situations in which the belief can be simplified? So, let me give two examples. So, the first example is linear quadratic regulator or linear quadratic Gaussian problems. For those of you who have taken a course in systems and control, you may have seen some version of this. If you haven't seen this before, don't worry about it too much. This is a system in which my dynamics are affine. There's some matrix, okay. I'll write it as A underbar. In control theory, people write A for this matrix. So, I'll just write underbars to denote these are matrices. So, you have some dynamics of this form. The control notation is different, that's why, but I don't want to introduce a new notation here. And my observation is some C matrix times the state plus perhaps some other noise. and you observe the output of the system, and you are interested in a per step cost, which will be F transpose Q S plus A transpose R A, where this is a positive semi-definite matrix, this is a positive definite matrix. Okay. Now, the interesting thing in this case is that one can show that the optimal controller is linear. Which means that I am going to be choosing AT as a linear function of my history. Once you do this, and I go back and look at my belief will be probability distribution of Ft conditioned on all my observations. And if I make the assumption that these guys are Gaussian, then if my controller is linear, I have a completely linear system of random variables. So, everything is jointly Gaussian. That means that my conditional distribution will be a Gaussian distributed random variable. This will be normal variable with some mean, let me call that f hat t given t, and some covariance. And a property of Gaussian random variables is that when I do the conditional mean, the conditional covariance does not depend on the data that I am conditioning on, right. This is a deterministic object, this is not a random variable. Therefore, in linear quadratic Gaussian problems, just the conditional mean is a information state. I can write down my dynamic program in terms of conditional mean. Rather than going through all this, we can start from the beginning and say, argue that conditional mean is going to be a sufficient statistic by showing properties P1 and P2. And once we have that, we can write a dynamic program and derive the fact that linear policies are optimal starting from the information state. Okay. I wanted to give one more example, but I'm out of time right now. So, let's stop and we'll give that example in the beginning of the next lecture and then continue. All right. So let's get started. I'll start with sort of this example that I could not finish last lecture, and then we'll start looking at approximate information states. So the purpose for this example is to try to illustrate that we can get useful information states which are not belief states. So the motivation is as follows. Sort of related to what I was talking in the previous example, but slightly different. So suppose I have a sensor, and this sensor can observe a Markov chain. Okay. So this is Markov chain that can be observed by the sensor. And now I have a receiver, and at every time the receiver has to make two decisions. The receiver has to decide whether to take a measurement from the sensor or not. And so what did I use the notation for that? So it has to take an action AT, which is 0 or 1. AT equals to 0 means that the receiver does not observe anything. AT equals to 1 means that the receiver observes the state of the Markov chain. So my observation is going to be blank. I'll just note it by this calligraphic E if AT is 0, and it's the state of the Markov chain if AT is 1. After having taken an observation, the receiver also has to generate an estimate of this underlying process. So it generates a second decision, which I'll call S hat t, and this will be some function in general of let's call it pi t. The notation I'm using in my notes is pi t t of all the observations so far, and I'll clarify what this is. And this is something which belongs to the space of this. So the idea is I'm trying to monitor something, right? So suppose I'm trying to monitor some temperature in an Arctic region. If I think of the power consumption of a sensor placed there. So clearly I want to conserve power because I don't want to go too frequently to have to replace the battery in an Arctic region. But there are two sources of power consumption. One is the cost of taking a measurement, and typically for most sensors this is something which is very, very small. The bigger cost would be taking that measurement and transmitting that over the air. So the sensor has to turn on a radio and transmit power over the air, and that would take about 2 to 3 orders of magnitude more power than it takes for sensing something in the ground, right? So I'm ignoring the power consumption in the ground and saying the sensor always has sensor readings available, and the sensor is not deciding when to transmit. The receiver may be deciding based on other factors when to take an observation or not. Okay? And so this is slightly more general than the generic POMDP because there are two decisions to be made. Right? So I'll call history at time t minus 1. This is the time at which the decision maker takes the decision AT, and this guy is the observations it has obtained till time t minus 1, actions that it has taken till time t minus 1. I'll not explicitly add the estimates it has generated in the past because it's clear that these estimates do not affect anything about the future, so there's no value in storing that. But I could have started by keeping that estimates there and showing that I can drop that because they are irrelevant according to Bellman's principle of irrelevant information. And h t given t is y1 to t a1 to t, right? So clearly from going from this to t plus 1, there is nothing that is changing. Only thing that is changing is that an additional estimation decision is taken, but I am not explicitly keeping track of that. Okay. And I am going to assume that I have a per step cost, which depends on the state, the action that is taken, and the estimate that is generated. And this cost is some kind of distortion between S and S hat plus some cost if I take a measurement. And this problem is trying to capture this trade-off between, just give me 1 second, it's trying to capture this trade-off between I can always take measurements, I will incur a measurement cost, and I'll have no distortion because I observe the Markov chain all the time, or I can never take a measurement, in which case I'm just doing open loop prediction of what the value of the state is, and I'll get a high distortion. Yes. No, I'm just, this is a notation which is popular in control theory. So I'm basically just saying, like, look, when I look at the time interval t, this is time interval t, there are two decisions that are to be taken here. This is a decision where I choose what AT is, and that determines what YT is, and after observing YT, I choose what S hat t is. Okay. So I'm calling this guy t given t minus 1 in the sense that the information that I had here was till t minus 1, and at this stage I'm taking decision based on the information that I have at time t. Okay. Now, I don't want to go into the complete dynamic programming decomposition of this problem, but let me just give at a high level what is going to happen. So I can clearly argue that the information state is going to be the belief. So I'm looking at what to do, whether to take a measurement or not. Okay? Because the other decision on what estimation to take, this is a filtering problem. I can just use the map estimate given the belief at this stage to compute what this guy should be. So I can solve the filtering problem separately, and I'm simply worried about what I have to do, when to take a measurement or not. Okay. So what will happen is that I can argue that my belief state is going to be probability that the Markov chain is in certain state given information y t minus 1 and a 1 to t minus 1. Now let's observe what will happen to the evolution of this belief for along certain sample path. Okay. So I'm going to draw this belief being lying in a simplex in 3 dimensions. And let's say when the system started, we knew what the state of the Markov chain was. So in that case, my belief will be a delta function centered at this part of my Markov chain. Okay. Now, when I do not take an observation, what happens to the belief? The agent has gotten no information from the system. So the belief would just be the how we compute the distributions of Markov chains. So if I do not take an observation, then the next belief is going to be, it depends on how I write things. I'm going to write it in the way we write things in Markov chains. So it's going to be the old belief, which was the distribution of ft multiplied by the dynamics of the Markov chain. Okay. This is what happens if I choose t to be equal to 0. Okay. What happens if I do take a measurement? Right. So if I don't take a measurement, this evolves. It's going to do some evolution in my belief state, which is just taking the old belief and multiplying it with the P matrix. Suppose after not taking measurement for 3 times, I decide to take a measurement. What will happen? I'm going to see one of the states of the Markov chain, right? So my belief is going to collapse to a delta function at one of the corner points. So this is going to be delta at some s with probability bt of s. If my belief said this was 1/3, 1/2, 1/6, then when I do get a measurement, I'm going to see, so it's not going to be this, it's going to be bt times p, right? I'll get the observation, but at this I'm looking at the belief at the next time step, so I'll have a multiplication with p. So when I get the observation, it will be one of these corner states. And next time that I'm taking a decision, I know the Markov chain has evolved in a certain way. Okay. So if I make an assumption that B0 is a delta function at one of the states, then what is really happening is I can capture everything about this belief in terms of what was the, let's say, let me call it ZT. This is the last observation, and I can say t minus tau. This is the time since the last observation. Okay. And this ZT would be equal to the state that I observed at the time tau, if tau was the time at which I took the last observation. Okay. So in order to compute the belief, it's sufficient for me to know how much time has elapsed since I took the last observation, and what was the value of the state that I observed when I took the last observation. And I should be able to write down a dynamic program in terms of these objects. Okay. So I can show, let me just not use ZT here want to use that for information state. So let me just call it S tau t and t minus tau t, where tau t is the time I took the last observation. Then I can claim that this guy is an information state. So this is a much nicer information state than the belief state, because it is a countable set. It has some nice structure. I can easily do approximation. If I say I'm going to implement a policy which says I'm never going to wait more than 100 days before I take an observation, then this lies in a finite set, and I can solve this very, very easily. Okay. But this is an explicit example of an information state. I mean, it is effectively the belief state, but the point is I don't need to work in the space of beliefs. I can simply work in the state of countable state Markov chain and figure out what the optimal policy is. So f hat is just, right, so if at some stage I have a belief Bt, your f hat t should be the minimizer over all f hat, summation over s, belief of s times distortion between s and s hat. Right? This is my map estimator given the belief. Yes, so I can reconstruct the belief from this, right? So in order to do that, I can reconstruct this. In fact, I can do much better, right? I can, in a real world implementation, I can pre-compute this for all values of my states that I'm going to encounter, and I don't have to resolve this optimization problem every time. I can just store these numbers. So here the belief is going to be delta at s tau p to the power of t minus tau. Right. So there is, if you think about this, this is now when I'm multiplying here, I'm looking at one particular. This gives me, this is a row vector multiplied by a matrix, and I'm doing a column vector to get an element. So I can write this whole thing as p to the t minus tau multiplied by this distortion matrix. So there are computationally nice ways of doing this computation to figure out what this thing is. Okay. But without going into too much detail of how to get a complete solution here, the point I want to emphasize is I can have models where my information state takes much easier form, right? So we looked at LQG towards the end of last lecture, where my information state was just the conditional mean. This is an example where my information state is specific to this model, and rather than necessarily going through this thing, I could have just from first principle argued that this is going to be an information state and directly written down the dynamic program. Okay. Any questions? When do we actually, sorry? I'll solve the dynamic program for that, right? So I'll solve the dynamic program. It will be a function of what these distortion functions are, and you basically what's going to happen in my simplex is I'll get this region, some convex region inside my simplex. I will sample the first time my trajectory enters this convex region. When I'm outside this region, I'm sort of close enough to the corner that my error that I get from this is, I mean, roughly speaking, it is less than the cost of taking one observation, which was where I wrote down the cost. So, I mean, it's not precisely that, because it also depends on the impact of taking a measurement on the future and so on. But that's kind of the thing. I'm trading off whether to get low distortion by paying a high cost for taking an observation, but this reduces the distortion now and reduces the distortion all the time in the future, right? Versus if I do not pay this cost, I incur higher distortion now and I incur higher distortion all time in the future, and the dynamic program, the value function, captures that trade-off. I don't think so. I mean, I have, it will depend on the dynamics of my Markov chain. So something like entropy is not going to be sufficient. Even if I take the entropy of the Markov chain type of thing, those are not going to be sufficient things here. Yeah.
So in some sense, I can think of it as we start at some corner of the simplex, and then suppose we don't take observations for some time, we'll move further and further inward to the simplex.
Yeah.
And then we take the distribution, we collapse to a corner.
Precisely.
And then
Yes. Yeah. Right. So if this Markov chain was ergodic, had I kept on taking this, not taking any observations, eventually I'll go to the stationary distribution, right? So if my this cost was too high, I can just go to the stationary distribution and say that's I'm only going to guess based on the stationary distribution. But if this cost is sufficiently lower, then I don't need to wait that long. I would rather keep my distortion much less. All right. So this concludes the discussion on sort of information states. Next, what I want to look at is approximate information state. Which I'm going to call this as AIS. And let me give the motivation via an example, and I'll come back to sort of this example probably end of this class or next class. So suppose I have a MDP. So this has some state and whatever. And I have an agent which is controlling this, but it's taking observations over a wireless channel. Okay? I did a very good job designing a good communication channel, but there's some small probability P that my observation is going to be dropped. Okay? So my observation, most of the time, my observation is Ft with probability 1 minus P. Occasionally, I don't get anything. Okay. How do I choose optimal control actions? So I can do the standard thing. This is a POMDP. I can set it up as a POMDP, maybe the type of things we were doing here. This is going to be some belief is going to be some delta function times the amount of time I have not received this. But like if you talk to an engineer, this is not what they will do. Okay? If you are an engineer, how will you design the controller for this system? Especially if I have a very good channel. Sorry? Yes, I'm simply going to say, well, I don't care. 99% of the time I'm getting the right observation. I'll just figure out the MDP policy and I'll implement it. Okay? There'll be some error. If P is small, that error is going to be small. Okay? So I want to argue if I do something like this, can I quantify how much am I going to lose by doing something like this, right? And that's kind of the motivation. I'm not going to come up with an approximation scheme based on some mathematical reasoning, I have some intuition about how the system that I'm modeling works. And that intuition tells me here is a policy. It's not necessarily optimal, but it's based on some intuition. And I have a strong reason to believe this is going to work reasonably well. I just want to make sure it's not a terrible policy, right? So I can do that by, if I have the ability to solve the problem exactly, I'll solve the problem exactly, and then I'll compare how well this is doing. But what happens if I could not solve the problem exactly? Can I still quantify how good or bad this thing is without knowing the solution of the optimal problem? Right? So that's what we want to develop. And what this boils down to, going back to the generic model that we had, is that I have a POMDP, and I'll consider this in the general history-based setting, and I'll call that we had given a dynamic program which I'll call history-based MDP or history-based dynamic program, which you recall was this object, right? Q star of t plus 1 of ht plus 1 is 0, and for all t, we were doing q star of t ht at was expectation of ct plus vt plus 1 of ht plus 1 given ht and at, and computing v star t of ht to be equal to minimization over action of q star t of ht. Now, what am I doing in this example? Okay. I am saying that I am going to take the history, I am going to come up with an approximate information state. I have a function sigma which maps my history to some abstract space. In this case, if I get the state perfectly, it is the value of the state. If I get a blank, I'll still have to act there. So I'm going to pretend when I get a blank, I'm getting some nominal state of the Markov chain. Okay. So I come up with this thing. This is completely made up, right? And now I say, I'm going to compute a policy in the space of this AIS. In order to compute the policy, what I said here was, I'm going to use the MDP policy. That means I'm going to completely make up a cost function here, and this cost function is going to be z cross A into R, and I'm going to make up a dynamics, which is z cross A into delta z. In this example, these are the cost function and the dynamics of my MDP. But this doesn't have to be the cost function and dynamics of my MDP. It is just something which I think are reasonable dynamics for this made up thing. I'm completely making up an optimization problem. Okay. But my intuition is, if in some sense this AIS is close to the true information state of my system, then what I do here should be close to the optimal policy. Okay. So in particular, I can think of this history-based MDP as the true model of the world. Okay. And I just made up a completely artificial model, which is M hat. This model is with state space Z. It has cost function C hat. It has dynamic P hat. Okay. This is an MDP. This is also an MDP, right? It has state space which is changing over time, but that doesn't fundamentally change anything. The reason we made an assumption state doesn't change over time, or state space doesn't change over time, was just notational convenience. There's nothing in the theory which said my state space should be time invariant. Okay. So, and what I'm interested in doing is, I'll take this thing and I'll solve a dynamic program from this, and I'll get a policy. In my example, I solve the MDP and I get the MDP policy. And what do I do in my real system? I get a sequence of observations. I compute the AIS corresponding to that history. In this example, if there was no packet drop, that's the current state. If there was the packet drop, then that's the nominal state. I'll go to my policy and I say, how will my policy act there, and I'll use that. Okay? So what I want to do is I have now a policy pi, which is equal to pi hat composed with sigma. And this means that pi t is pi hat t composed with sigma t. And I want to see what is the loss of performance if I use this guy in my original model. So apart from the fact that these history compression functions are varying over time because the domain is changing over time, nothing has changed from the problem we did yesterday. I have an MDP, I construct an abstract MDP, I find the optimal policy for an abstract MDP, and I want to know what's the loss in performance if I use it in the original MDP. Okay? So I already know how to do this. So I can simply take those results, use it here, and I'll be able to quantify what is the loss of performance, loss in performance. Okay? That's it. Okay? All I have to do is quantify what is the degree of closeness of these models, and we had results which from that told me what the approximation error would be. Questions? So this is the main idea. Rest of it is just bookkeeping. Okay? Because I'm just going to translate all the results we did last time into this setting. But key point is, conceptually, approximations in POMDPs are no different than approximations in MDPs when I go from one state to another. And all results will transmit directly. So let's make this a bit more concrete. So I'll start by defining what I'll call an AIS generator. An AIS generator is the collection of sigma t, c hat t, and p hat t for all times. And I'll use the say zt to be equal to sigma t of ht. I'll call this an AIS. Okay? Or sometimes I'll talk about the AIS process. So I have an AIS generator. This gives me an AIS, and I want to say how good an AIS this is. So we'll do the same thing that we did for model approximation. So given a sequence of real numbers epsilon 1, epsilons and deltas, I'll say zt is an epsilon delta AIS if two conditions hold. Okay? And these conditions are same as what we had for abstract MDPs. I'll write them in full rather than in the vector notation, but I want call this AP1, comparing to what we defined as property P1 for the MDP. This is the for an information state. This is the approximate version of that. I have the cost at time t. I have the expectation of the cost at time t conditioned on ht and at minus c hat t of sigma t of ht and at should be less than equal to epsilon t. Okay? This should be true for all ht and at and for all t. this is how we had defined epsilon in the MDP epsilon delta model approximation. But to me, the interesting way to look at it is, if these epsilons were 0, this is exactly P1. Right? In P1, I wanted this to match exactly. And now I'm saying, rather than having exactness in my first property of an information state, I have some looseness, and that looseness is measured by this epsilon t. And I'll define AP2. Now, I'm doing the same thing for the exactness in distribution. I'll say, instead of being exact, if I have approximately match in distribution, then I'm okay. And I'll have to take that approximation with respect to some measure on probability spaces, and I'm going to use an IPM here. Okay. So I'll use some IPM, and I'll say the probability distribution of ZT plus 1 conditioned on HT and AT times what is the probability distribution, this is at time, probability distribution at time t of ZT plus 1. Let me write it like this to be clear that I'm talking about distributions here. Given sigma t HT and AT is less than equal to delta t, again for all histories and actions for all time. Okay. If these two properties hold, I'm going to say my AIS generator is an epsilon delta AIS. Okay. And at this stage, it should be clear where we are going from this. Once I have this, I almost immediately have my approximation bounds. Okay. So from what we did in the in yesterday's class, the only small difference is there we were assuming the state space of the original MDP was not changing over time, and these functions were constant over time. But that was just for notation. There is nothing fundamentally that these things needed to be time invariant. So when I go to this setting, the results are going to translate exactly. So what I'll get is, I'll just write down the result for model approximation, because that's the final thing we care about. I can ask the following question. If I look at the value function of pi hat composed with sigma, okay, that's the policy that I defined there. I find the optimal policy in my AIS model and use that policy in my true model, and I ask what is the error in this compared to the best that I could have done. Now, the best that I could have done here now is the best for the partially observed system, best for this history-based DP. If I look at these at any times, so let me sort of explain what I mean by this, just so that it is clear. This object is really equal to the soup over all histories, absolute value of V pi hat t for that history minus V star t at that history. Okay. Remember, this gives me a policy which is history based. So I can go back to my history based DP, and I can do policy evaluation for that. And I'm saying what is the difference between these two at any values of history, and that's what I mean by the definition of soup now. So the soup is over all histories. And what we will get is what we had obtained last time was that this was less than summation of tau equals to t to capital T. We had defined this model mismatch operator times V hat star t plus 1. The same result holds. It's just a question of what my model mismatch operator was. Okay. So recall my model mismatch operator for any V hat was given by the dynamics operator applied on V hat. And now what's going to happen is these things have to be time varying, right? Because the domains of things are different. So V hat does not have time varying domain, but this will be in the Q function of the original model. So, I will have to get something which is time varying. So, I will say this is V hat composed with sigma t. V hat composed with sigma t gives me a history based value function, and I can do the one step evaluation here, minus E hat t applied at V hat. This gives me something which has Z A as an argument, and I compose this with sigma t. So, the change from last time is these compositions are time dependent, right, and that is it. So, this is not a perfect result, because this requires me to be able to do this environment operator on this model, right. So, I would need the ability to do some calculations in the true model. If I cannot do this thing, what we had shown last time was also that this is going to be upper bounded by twice summation t equals tau equals to t epsilon t plus delta t rho f of V hat star t plus 1, right. These were the IPM based bounds. Yes, thanks. Okay, that is it. So, I can get very, very easy bounds for approximation errors in POMDPs. Just if I have an approximate model which has some dynamics and cost, then I can say what is going to be the difference of that dynamics and cost from the true cost and the true dynamics, and based on these errors, I can get a bound on how good of an approximation this is. Okay. Questions? So, let me talk about few variations of this. So, one of the motivations for trying to understand what happens in these types of scenarios was to see what happens with learning algorithms in POMDPs, where our thinking was that a neural network is constructing some kind of history compression function using a recurrent network. Okay. But what often happens in these neural network architectures is that you do not want to keep your state update to be a deterministic function. You often keep that as a stochastic function because those smooth dynamics are easier to learn or not. So, at this level, I can ask the following. So, what if ZT is stochastic? Okay. So, typically what you would do is you would do something like what we were calling in P2A, that ZT plus 1 will be some function of ZT, YT plus 1, AT, and some randomizing random variable UT. Okay. So, what happens if I was doing a stochastic AIS? What will happen to my bounds? Sorry? We do not need to do this, but people who implement the algorithm do implement it in a stochastic manner. And the reason is, if I was learning something like this, right? So, what if this was a discrete object and you are doing a machine learning algorithm to learn the best AIS type of thing or best update for the AIS, what you would do is you would think of this as a transition matrix, which you would do something like a softmax, and then you would learn the weights of that softmax according to a gradient descent algorithm. And because I'm making this update to be softmax, inherently there is some randomization which is happening there. Okay. So the thing to realize is, if I'm doing this randomization, abstractly I can think of this randomizing random variable as something that I observe. Right? I observe this random variable and then I decide where do I have to jump. So I can just think of ZT comma UT as my AIF. Okay. So nothing really changes in my analysis. The dynamics, the cost part remains the same, because this randomizing random variable is something completely independent of what's happening in the system, so it's not going to affect the cost. It's going to affect the dynamics, but since now I know what's the update going to be for every realization of U, this effectively is the same issue. Right? So some of the expressions become slightly different, but conceptually nothing changes if I have stochastic evolution of my information state. It is not something I'm controlling. Yes, and what I'm saying is this is an exogenous process. It's not an endogenous process, because if it was an endogenous process, I'll optimize over this. Right? I'm not optimizing this sampling. Okay. Second question. If I'm running, so let's say I'm designing a robot. This robot has a camera attached to its head. I'm doing some sort of motion planning based on this camera. Okay. I would not like to construct an AIF based on this raw video feed. Okay. That's just super high dimensional object. What I would probably do in a real system is I'll take this image, I'll pass it through some image segmenter and so on, and I'll abstract out what are the key features of this image. The image maybe has a path, has some chair, table, I can see some people and so on, and I would segment out all of that, and I will pass that feature onto my history compression function and then work with that. Okay. So what happens if I want to make decisions not based on yt, but I have some y hat t, which is some quantized version of yt, and I want to work with y hat t. How should I quantify what is the loss in performance that I will get if I'm working with y hat t rather than yt? Again, conceptually, this changes nothing, because what I can think is, look, I had this system. This was taking wt minus 1 and at minus 1 as inputs, and it was giving me ct minus 1 and yt as outputs. And I can say there is this other system, which is this quantizer, which takes yt and gives me y hat t. And from my system designer's point of view, this is the entire system, and I'm going to choose an agent which does some compression of these quantized things. Right? So taking this view, nothing has changed. I'll just have to say this sigma t was a function from compressed or quantized observations to some abstract space. My definitions here would remain the same. Okay. So if I can quantify what happens, so this becomes essentially sigma t becomes whatever I'm having. My sigma t is a function from quantized histories to z, and I'll think of sigma t composed with q as my history compression function. So, wherever I am writing sigma t, I will write sigma t composed with qt. Okay. So, let me give one more illustration, one more variation, I am sorry. So, what if I were quantizing the actions? Again, suppose I am designing this robot, the robot is moving around and I have to control the angle at which the head should face. That is a continuous valued decision variable, and I decide that I am only going to move the head in increments of 5 degrees rather than an arbitrary amount. Okay. So, now I have something which is slightly different, because we are in a setting which we have not discussed before. Okay. But nothing really changes conceptually as long as I am in the action quantization regime. So, I am assuming there is some A hat, which is the space of quantized action, which is a subset of the space of all actions. Okay. So, what will happen now is that my AIS MDP will be defined on A hat, right. So, I will have C hat, which is going to map Z cross A hat to R, and I will have dynamics P hat, which map Z cross A hat to delta Z. Right. The interesting thing here is that once I take this AIS model and I get a policy, okay. So, in the end I will get a policy. This policy at time t is going to take Z and give me something in A hat. Okay. The key observation is that pi hat t composed with sigma t, which is something which will take me a history and give me an A hat, is a valid policy in the original model. Okay. So, what I am interested in is asking what is the loss in performance if I use this policy in the original model. I do not have to do anything with my actions. When I use this policy in my robot, the head will move in increments of 5 degrees, and I just want to see how good or bad that is compared to the best that I could have done. Okay. So, the way I would model this is that I am going to say there is a function, quantization function psi, which looks at the action and gives me the quantized action. Okay. And when I get to an equation like this, I will replace AT with psi of AT. And here I will replace AT with psi of AT. That is it. Okay. So, now I want to say, instead of using the actual control that I could have used, if I use the quantized version of the control, how much do I lose? And same thing, rather than the true dynamics, if I actually use the quantized control action, how much do I lose? And once I quantify both of these things, my bounds are going to remain valid. I will get the same exact bounds. So, action quantization is going to change my model error. Okay. But beyond changing the model error, it does not change the nature of bounds that I will get. Okay. Any questions on these? Okay. So, one other thing that I want to discuss here is this guy is based on property P2. Can I get some approximation error if I was doing an approximation of P2B, right? So, if I have an AIS which is recursively updatable, and I can figure out how good a prediction of the next observation it gives, can I get some bound on how good a prediction of the next AIF it would give? Okay. So, let me write that down here. So, I am going to assume P2A. So, I will say ZT plus 1 is some function of ZT, YT plus 1 and AT. And I am going to say P2B, which is the IPM distance between the probability of the next observation given HT and AT times I have some different kernel, let us call it P hat T y, which gives me YT plus 1 given sigma T HT and AT. Suppose this guy is less than equal to some quantity, let me call it delta T y. Okay. Does that imply that AP2 will hold? And it turns out that I can get this bound. I can show the following. I can show that P2B implies P2, but delta T is going to be equal to delta Ty multiplied by some property essentially of sigma T and phi. Sorry, not phi, it is just a property of sigma T and phi, where phi is this object. Okay. I will not go into the detail of this derivation here, it is just basic algebra, because what was happening when I showed P2B implies P2, there was a series of equalities we were showing. Right? And now I just have to keep track of what is the error in each step in that, and that is going to depend on the smoothness of this function and the smoothness of this function. So, this expression is complicated to evaluate, but the key point is if this guy is small, then this thing will also be small. This is scaling linearly with respect to that error that I have. So, I can use this as a proxy to figure out a model where the prediction of the next step is small. But this is with the caveat that this can give me an information state which is bigger than the information state that I may get from here. Okay. Yeah. Just it is a different delta. So, I am just saying this is delta corresponding to y. Okay. All right. So, finally, when we were doing the bounds for model approximation, I said that these bounds are loose, right? Because in deriving this bound, inherent somewhere there is this triangle inequality, and that triangle inequality is significantly loose. And once I upper bound these guys with IPM based things, there is an additional looseness factor here. And to resolve that, what we did was that we derived these results which were based on sample path bounds. Okay. I can do exactly the same thing here. Right? The difference is going to be, again, my mismatch operator is going to depend on sigma t, and that is the only change I will get. I will get this joint recursion of an alpha upper bar, alpha lower bar, and based on those alpha upper bar and lower bar, I can quantify what would be the sample path based error between these two quantities without taking the norm. Okay. I am not going to do the derivation here, but really it is exactly the same derivation that we did last time, modulo this one change in the definition of the mismatch operator. Okay. So, the key point is once we start looking things in this way, POMDPs is really exactly the same thing as MDPs with very, very minor differences. Right? So if you understand approximation in MDP, you immediately get approximation bounds in POMDPs. So in the remaining time, I'll try to do 2 examples to illustrate how these types of bounds can be used. Okay. Before going there, any questions? So let's start with simplest type of approximation we can do in POMDPs, which is belief quantization. Okay. So how do I do belief quantization? The simplest way to do belief quantization is the following. Let me think of a quantized alphabet. This is the set of all PMFs. So let's say cardinality of F was equal to n, and let me call this m. So this will be a collection of numbers P1 to Pn. Okay. And I want to do belief quantization in such a way such that Pi multiplied by m is a non-negative integer, and P1 till Pn is equal to 1. Okay. This is the most natural way to quantize distributions. I quantize distribution, so if m is equal to 10, I'm quantizing distribution such that the denominator is 10 for everyone. Okay. And what you can show is, so clearly what I'm interested in is, let's call phi of b b hat to be the closest point in QM that corresponds to any belief. Okay. There is a lot of work in information theory, sort of those of you who have taken an information theory course, these are like type sequences in information theory, and there's a lot of result in properties of these. One of the things you can show is it's relatively efficient to find what the closest quantization point would be, and you can characterize what's going to be the L1 distance between B and phi of B. Okay. There's an exact expression of this in terms of n and m, but the claim I'm going to make is, well, if I make m large enough, I can make this guy less than equal to some quantization radius. Okay. That should be intuitively obvious. The exact expression we don't care about for the purpose of this. So now I have a quantization scheme. I can come up with dynamics of this b hat, and the dynamics of b hat that we'll come up with is really, I have a simplex, I quantize this simplex, this didn't turn out nice, but imagine I had drawn it nicely. So these are all triangles, and I'm looking at some point here, and I'll do the same thing that we did in quantization. I'll say the dynamics is going to be what is the probability from this point to going to that quantized cell. Okay. And you can show the following. You can show that the epsilon t that we are interested in with this model is going to be upper bounded by r times the span of Ct. This is relatively easy to see because epsilon t is in terms of expectation of cost with respect to the belief. So this part, the proof of this is, we have Bt of S times Ct of Sa minus summation of B hat t of S, Ct of Sa, and this is going to be less than equal to the total variation distance between Vt and B hat t times the span of Ct. So, I immediately get that my epsilon t will be less than equal to r times span of C t. Computing delta t is more complicated. It requires certain properties from information theory to show that, but with some algebra one can show that delta t is less than equal to 3r. Okay. In the notes I have given a reference to a paper with the derivation. For our purpose of our discussion, this part is not super important how we get that, right. But intuitively this should be, this makes sense. What I am saying is, if I have sufficient smoothness and I quantize things fine enough, then the dynamics that I get in this quantized model versus, so you see the question I am asking is, if this was the true belief state and I pretend that the dynamics are given by movement from here, what is the difference between the actual probability of going from this point to this cell versus the probability of going from the center of this point to this cell. And it is reasonable to assume that this probability is going to be a function of the radius of this cell. Okay. So, without figuring out what this factor 3 is, it should be sort of intuitively clear that this is going to be proportional to r. Okay. And once I have this, I can use these things to figure out what my approximation error is going to be. Okay. So, I can substitute it somewhere here. Had I computed the optimal solution of the quantized model, this is going to be my error. Okay. So, this allows me to figure out how good of a solution I have, having done quantization in the belief space. So, now let me come back to the example I started at in the beginning, and I will try to, the analysis there is a bit more detailed, and I will try to give some intuition on how would we go about getting a sample path based error bound there. Okay. So, recall what we wanted in sample path based error bounds was that I wanted a lower bound. So, I am going to translate that in the current thing. I wanted a lower bound which could depend on the entire history, but when we were doing state abstraction, I said ideally I want a lower bound which is uniform over this history and actions, so that C expectation, let us just call this guy Ct of Ht At. This is the expectation of the per step cost conditioned on the history, just slightly easier to write, minus C hat t of sigma t Ht At to be less than equal to epsilon plus of sigma t Ht At. Right? This was one bound that we had, and overall our expressions were then in terms of epsilon t and delta t. And we had a similar type of bound in terms of delta. Let me just focus on this and I will come to delta in a second. Now, notice what is happening in this model, right. So, this was my example where Yt is equal to Ft with probability 1 minus p, and this is blank with probability p. Okay. Let me use the variable dt to denote that there was a packet drop at time t. Okay. Now, when there is no packet drop at time t, this error is 0, right, because I get to observe the state exactly. It is only when there is a packet drop I have an error. So, the way I would like to construct this bound is to say, so what we were doing was, this was actually the actual cost at state Ft and action At, minus when I do get a packet drop, I said I am going to assume I am at some nominal state, let us say S nominal and At, and I want to get upper and lower bounds on these. rather than trying to get upper and lower bounds, so you see what I would have to do is this thing is the nominal state. So effectively, what my theory is saying is if I want computable bounds, I want bounds which are like this. Some epsilon and delta, epsilon plus and epsilon minus, which only depend on the action. In a practical system, if I want to really compute this will give me nice bound, but this is not going to be a good expression to compute, because I'll need to take expectations over the policy to see what happens to this. Okay. So what I'll do rather is I'll get upper bounds and lower bounds which do not depend on the action. Okay. So I'll take this guy and I'll take the soup of this over all ft and at, and that will give me what epsilon plus is. I'll take the inf over all of that, that will give me what epsilon minus is. Okay. That's a cruder bound, but it is something which does not depend on action. What it does depend on is I have separated out with the packet drop. Okay. So my final bounds are going to look like, I'll write this in the vector notation, Ct minus C hat t composed with sigma t is greater than equal to epsilon minus t times dt and less than equal to epsilon plus t times dt. So I'm capturing the fact that when I have no packet drop, the error is 0. When I have a packet drop, this error is something. This is now a slightly looser bound than the tightest I could have gotten, but I'm making sure this is not a function of action. These are just constants. So my calculations will be easier. Okay. And what I'm going to do with deltas now is the same thing. So with the delta, you see the actual thing that I had was that the IPM distance between the dynamics of the next information state, probability of z t plus 1 given dot conditioned on, this is a weird pen, ht and at, and probability of z. So what the dynamics that I have assumed now are, I'm looking at the dynamics of the MDP, and this would be the MDP dynamics phase. I'm going to go here, conditioned on sigma t of ht and at. Okay. And what I like to capture here is also the fact that when I do not get a packet drop, this object is 0. Right? Because I observe the true state, so the next observation of the true state of the system is going to be correct. It's somewhat ugly to characterize what this thing would be if I did get a packet drop, because that will depend on how far is the actual state of the system from my nominal state. Okay. But what I can do is, let me take something like total variation. Okay. Then I know this guy is going to be less than equal to 2 if dt equals to 1. That's the maximum value of total variation. Okay. So I can take delta t to be equal to twice dt. Okay. So in my expressions, so notice we had this complicated recursions in terms of alphas and betas and so on. I don't want to go into all of them, but the key point was I had things like beta t plus 1 is either greater than equal to or less than equal to epsilon t plus delta t rho f of v hat star t plus 1 plus the hat dynamics on T of alpha T plus 1 plus delta T times rho f of alpha T plus 1, right. These were the type of expressions that we had. And what I have effectively done is that I have taken all these random variables and made sure they depend on dt. Okay. I have gotten rid of the dependence on the state and actions. And so, when I am doing this probability averaging, only thing that will matter is whether I got a packet drop or not, okay, which is an exogenous process. So, I can compute these bounds. Okay. The expressions are going to be slightly ugly. In the notes I have given the expressions, but the main point is not sort of deriving that expression, right. If you are interested in this application, we can derive the expression. The point I want to communicate is that the advantage of the sample path bound is I can, this is very, very model specific thing, right. I can figure out what is the, I am trying to get an upper bound which I can compute with as little information about the model that I want to choose, and I have done it in such a way that it is computable and it is also going to be reasonably tight compared to taking soup norm bounds. Okay. So, that kind of illustrates how we can use these sample path bounds with partially observed models. Okay. And one thing which will be clear from this entire analysis is that clearly as dt becomes close to 0, all these bounds are going to go to 0. So, I can even quantify the rate at which my error is going to depend on dt. Okay. Eventually, everything will be proportional to dt here. These things I am taking average, so I will have some kind of average which depends on p. So, the overall thing will depend on whether p is 0 or how big p is. Questions? Okay. So, this more or less completes what I wanted to say about approximate information state. What I will try to do tomorrow, let me kind of explain that. So, the type of approximation that we are doing here can be thought of what in the control literature is sometimes called certainty equivalence. So, you see in general the POMDP theory says that when I get partial observations, I should go from solving MDPs which are relatively simple to solving this complicated problem which requires updating of belief and all those things, which becomes super difficult. Okay. But if you look at implemented systems, people, apart from some specific applications, people do not implement this belief based strategy. And the reason is really what is happening in this example, right. If I have an observation channel, but my observation noise is small, I am just going to pretend that the observation noise is not there. Okay. And that is going to give me some errors which are going to be proportional to my observation noise. Okay. So, we are going to define these types of approximation schemes where I can, rather than working with belief, I am going to say I work with a state estimate based on the belief, and I will say given a state estimate, and I will use the MDP policy as a function of that state estimate and try to quantify how good or bad the approximation bounds are. Okay. So, we are going to do that derivation for the certainty equivalent policies in the first lecture, and then I will talk about some of the possible other type of things which this theory allows one to analyze and maybe open the floor for discussions, right. And we are a bit early, but I think we should, if there are any questions, I can take them now, otherwise we can stop. All right. So, let us stop then.